Hi, LT. How are you? We'll have 5 more minutes to wait and let people arrive. Thanks for coming. Sorry, I was muted. Hi, Ash. How are you? Thanks for coming. We'll wait like 4 to 5 minutes and give people some time to arrive, and then I'll introduce you to the audience, and then the stage is yours. Can you hear me? Hi, Frank. How are you?
Hi, Katerina. This was a very interesting subject. Looking forward to Dr. Salamat share.
Yep, me too. I'm pinging people in and share it on Twitter and so on. So, hi, Rahim. How are you?
Hello.
Thanks for coming. Meet Dr. Ash Salamat. Ash, meet Frank and Rahim, our team members, moderators.
It's nice to meet you, Dr. Salamat. Can you hear us? Hello.
Stop here. He just wrote me.
Oh. Oh, maybe
Oh,
going out and coming back in.
okay. Let me write him. Okay, he will try. Hi, can you hear us now? Still no?
You should maybe leave the app and come back. Like close it and then open it up again.
Oh, yeah, if he is. Oh, he's not on university Wi-Fi.
Hey,
Hi,
can you guys hear
Serena.
me?
Yay.
Yes.
Oh, there we go.
Hello.
Right.
Okay.
Perfect. Good that we were here earlier. Let's wait like a couple more minutes.
That
I didn't have a chance to really share the room.
that's okay.
And,
I'm just happy you can hear me and I can hear you.
yep.
Yeah, we're just saying hello. How are you?
I'm good. I just want to highlight that the fact that I can't use my phone can only mean I'm a great scientist.
Yes, exactly.
Yes.
We should not be good in social media. So I'm a crappy scientist. No, I'm not good at it. Anyways,
I'm the worst.
yeah. Dennis wanted to also come, so let's wait for Dennis, and then we can soon start.
Hey.
Meet Serena.
Hello. Yeah, I'm looking through the paper and I even checked it was one that you authored.
Are you referring to me?
Yes. No, I had an embarrassing moment where there was a different paper up and I started asking the guest speaker about,
Oh,
I
I
was
haven't
going to
checked
lead
this
up to
paper.
figure 4.
Oh, well, I had to quickly read the paper myself to remind me what my students actually do in my lab. So we might have both read the paper for the first time today.
Well, that was totally my mistake. On Saturday, we had the introduction meeting right before to onboard a scientist on Clubhouse, and then we switched over to the room, and I still I thought I copy pasted the next paper in my notes, but apparently I clicked on the same again and posted, and then I didn't really realize until people and it was like 40 minutes in, so that was a total fail. But it never happened to me before. But anyways, so how is your day going? Everything good?
I'm surviving. It's just, when you're doing front-end science, it's just never ending. So yeah, it's going very well. I mean, I'm married to my job, so every day's a great day.
So you're in a good marriage. That's good. Most people,
Yeah.
let's be honest.
Everything you
It's
just
highly
said.
platonic. It's highly platonic. So we have boundaries imposed. So it works
Everything
very
you just
well.
said is so relatable.
It's so funny.
It's like I'm surviving. I'm like, oh my gosh.
Okay, let's start with the introduction, and we'll go from there. So welcome everyone to the Science Society. We are very honored to have a really amazing guest speaker today, who will talk about his really cool research in exogeology. And let me tell you a little bit about him. So, Dr. Ashkan Salamat, he's an assistant professor of physics, and he did his master in science and chemistry at the Imperial College UK, and then he did his PhD in physical chemistry at the University College in London, UK, and he is currently at the Department of Physics and Astronomy, and he is also part of the UNLV's High Pressure Science and Engineering Center, which is a multidisciplinary group that explores fundamental experimental, computational, and engineering problems of materials under high pressure. His research focuses on identifying precise makeup of metacyperhydrides,
That's
extremely
good enough.
hydrogen-rich materials, and also techniques to synthesize them. So yeah, his lab, you can check it out. It's the Salamat lab at UNLV if you want to check out more about his research. And yeah, thank you so much for being here. Welcome. And if that's okay with you, usually Dennis or Victoria, today it's Dennis, ask like more like a general question first, and then you can go ahead and tell us about your work.
Cool, brilliant. Thank you for that kind introduction. So I'm going to start off by saying this is work done by my graduate student, Zachary Grand, who's an absolute superstar. And I'm taking his thunder and giving this introduction to our group. So I'm the recently appointed director of the center at UNLV, and really what we specialize in is we have this ability to make materials that Mother Nature herself cannot make. And what makes my subset of physics quite unique is we're able to modulate pressure and temperature in such a unique manner that we can overcome many of the barriers that Mother Nature herself faces. The big thing we're into at the moment is we're making high temperature superconductors. So we're bringing quantum materials to everyday devices. But the focus of this talk and the paper that's been highlighted by the group here is we have this ability in our laboratory to replicate the interior of planets. So this is quite a startling statement, really, but it's absolutely true. And I'm going to give you a very broad stroke of what we get up to, why we do it, and the importance of Zach's work in understanding the fundamental physics of water, the water cycle in the Earth, and its absolute necessity of understanding this as we try to extrapolate life in exoplanets. And what does it mean when we look at data at the Kepler mission and stuff like this, and trying to understand where water-rich planets could come? This sounds very grand, but really it's all accessible by this unique experimental technique that we've developed in our laboratory. Okay, so where should I start my journey? I'm going to start far afield and bring it back. Hopefully it's going to connect in some smooth connection there. So
before we begin, I'd just like to start with saying Salam Ashkan. And
bam.
We have a question here that we like to ask of
Do it.
scientists before they get into the meat and potatoes. I wanted to ask, what was the first step on your journey to science, or when did you know that this was what you wanted to do?
Oh, I love Q&As like this. Okay, so I come from a refugee family. We're ethnically Iranian. I grew up in London, and so I went to state school and so on and so on. And so I realized quite early on that the only way you could jump your socio-economical class is by being good at school, or by trying to achieve well at school. And so from a very young age, I was good at math, and I was lucky enough to have parents who, although were very educated back home in their native country, were unemployed at the time in the UK. And so I had a lot of parental privilege at the time. And so my journey as a scientist started quite early. That being said, just really quickly, I hate these stories about I knew at 5 years old I was going to be a scientist, and I didn't really know what I was going to do until I was like 25. I wanted to be a rock star for a long time, but I knew from a young age that education was the way to break out socio-economical classing. And so seriously, up to about the age of 25, I wanted to be a heavy metal rock star. I realized that a PhD pays more than working at Blockbusters, and so I took that up. But there was an underlying love of sciences and mathematics, and it was evident I was pretty good at it from a young age. There you go. I hope that answers that question.
Yes, that was a great answer. Love it.
Yeah.
With that,
Yeah.
go ahead, and if you have any other comments, go for it. And if not, then we can get into the presentation.
Boom. Okay, so I'm going to start really, really big and bring it back to the laboratory. When we look at the observable universe, most of the universe, 99.9999% of the observable universe exists as a hot plasma. A plasma is the state of matter you get to when you heat a gas to very, very high temperatures. You ionize this gas. Our star, our sun, is a giant ball of plasma. When we look across the universe, we mostly only see stars. And so most of that is just giant balls of plasma, predominantly hydrogen with some helium. Of the 0.00001% of condensed matter, a non-plasma state, most of that, in fact, is liquid metallic hydrogen, which is a mind-blowing realization. Jupiter and Saturn, and I showed this work when I was a postdoc at Harvard under the supervision of Isaac Silvera. Jupiter and Saturn are giant balls of liquid metal hydrogen, which is just mind-boggling. When you take something like hydrogen, which exists as a gas at atmospheric conditions, and when you cool it down, it solidifies at about 20 Kelvin. Pardon me, it does not. It solidifies at about 13.8 Kelvin. When it solidifies, it looks something like glass. It's what we call a wide bandgap insulator. you take this glass-like clear material, which is solid hydrogen, and when you squeeze it to conditions beyond that you find at the interior of our Earth, hydrogen metallizes. It becomes a metallic solid. What we showed with my work a few years ago is when you heat hydrogen to conditions comparable to that you would find in Jupiter and Saturn, it liquefies. It goes into a liquid metallic state. And the reason Saturn and Jupiter have all these weird quadrupolar magnetic fields is because unlike the Earth, where we have a solid core and a liquid outer core, and the dynamo effect between these two drives a magnetic field, in these giant gas giants, which are actually giant balls of liquid metals, there's localized turbulence, and this leads to localized magnetic dynamo effects. And as a consequence, you get very weird fields. And so I've been working on this for a very long time. It was all very exciting. Hydrogen, physicists love hydrogen. Everyone works on hydrogen physics. And when I got my gig here at UNLV, we had a specialized center that was dedicated to the kind of physics that I'm interested in. And I was like, man, I really should work on water. It's fundamental to life. It's, a little bit more complex than hydrogen. Let's go for it. And
It's
so,
kind of a big deal, yeah.
yeah, we have a running joke, and Zach does it very well. He's like, water, you drink it, you swim in it, you ski on it. And so we were like, okay, and actually the stories are more complicated than that. We wanted to do something called the synthetic Uranus recipe. I can never say that word right, but that name. So this is this idea that you take water, ammonia, methane, you make these balls of mixtures, you manipulate them in the laboratory, and you try and get an understanding of how these ice giants are formed. When we started our preliminary studies, we realized that most of the literature probably wasn't correct. And that's just the way science works. It's dynamic, you do a lot of work, and in 10, 20 years' time, understandings deepen, techniques evolve, and the status quo is most likely maybe not correct, but too basic in its understanding of nature. So we chose water. Now, what does the lab that I work in specifically do, and my super team of students and postdocs? We utilize diamond. So we have it's a handheld device called a diamond anvil cell. This has 2 gem quality diamonds, and diamond is the hardest known material we know on Earth, macroscopically anyway. We take samples and we squeeze them between 2 diamonds. And since diamond is so damn hard, you can squeeze stuff to incredibly high pressures. So we can exceed the pressure of the interior of our Earth, which is about 3.3 million atmosphere. And because diamond, as you can tell, is optically transparent to most of the electromagnetic spectrum, we can utilize lasers or light of different colors to directly look inside of our diamond anvil cell. So not only can we squeeze materials, but the transparency of diamond allows us to also look at these materials while under huge amounts of pressure. And this is where our journey starts with Zach. We decided to squeeze water and try and do a decent job and stand on the shoulder of giants and add to our knowledge of water. As we began our studies, what we found is water is a difficult mistress. It's difficult to handle, and I'm not talking water is easy to pour, right? But there's issues with it in the laboratory. And when you squeeze it, so when I take a liquid and I apply some pressure to it, I solidify it. Now, water, she's a complex entity. When you squeeze it, it doesn't just make a uniform powder, a uniform solid. So solids can exist as single crystals, they can be multiple little crystals, nanocrystals, and so on. When you compress water, it nucleates in a very specific way. There's quantum phenomena that drives the nucleation process of water. And it nucleates pretty poorly. It makes a pretty crappy crystal. And what that really means inside the confinements of a diamond anvil cell is that because you have this poor crystal, then the statistics in which you collect about this crystal are pretty poor. And what we found doing these experiments was like, wow, man, these folks, these boys and girls publishing for the last 40 years, they've been collecting some pretty damn poor data. There is such poor statistics in this data that it's very hard to make quantifiable conclusions from this. And so we were like, okay, cool. Everyone's done this. We've got to try something differently. What can we do differently? So In the previous life, I was a synchrotron scientist. A synchrotron is a large electron storage ring. The Large Hadron Collider, which I'm sure most of you heard of, is a particle accelerator where you try and achieve the fastest speeds possible to achieve the highest energies possible in the tera-electron volts. A synchrotron is like a poor man's version of a linear accelerator. Instead of being circular, it's polygonal. And what you do is you accelerate electrons really, really fast, and then you change their direction. And through Maxwell's equations and conservation of energy, as you change their direction, they spit out light. And the light you get at a synchrotron is twice as bright than that of a star. So these synchrotrons are about the size of a football pitch, and our samples are about 1/10 of the width of a human hair. So we go to one of these apparatus, and what we're allowed to do with these synchrotrons is we can shine really, really bright lights at these samples, and this light interaction with our sample can allow us to do certain techniques. And the technique we're interested in is X-ray crystallography. We shine light, photons, that have lengths that are comparable between the interatomic distance between atoms, and because the lengths are comparable, they scatter off these bonds. And so we can construct an atomistic picture of our material. This is a very common technique discovered or developed heavily by the Bragg father and son combo who won the Nobel Prize in the early 1910s and 20s. We've known this technique for a very, very long time, but now we're able to generate such bright brilliance, so large amount of photons, that we can look at very, very small samples. And so maybe the caveat I didn't add for the diamond anvil cell is that our samples are very, very small. So we have the sample inside 2 diamonds. We're going to this synchrotron, this bright X-ray source, to try and build an atomistic picture of the periodicity. How the hell are these atoms arranged relative to each other? As I said, the way water nucleates is very poorly, and so we get very, very poor powder averages. And so we were like, man, we've got to change this game up. We've got to try something new. I've been working on a special technique called CO2 laser heating. This allows us to excite CO2 gas, which in turn emits radiation, so photons, which are about the same color as the radiation we emit from our skin. So we glow. We're about 300 Kelvin, 100 degrees Fahrenheit, 37 degrees in real units Celsius. We glow. Everything glows that has some heat to it. And this CO2 light glows at the same color we glow at. And it's really easily absorbed by water. Water loves it. And so we were like, man, what if we shine very powerful lasers onto our water sample to try and disrupt the nucleation process and try and improve the quality of the crystal so that we can actually do some quantifiable measurements at this huge synchrotron thing. Sounds super easy, but no one had ever built a CO2 laser heating system at the synchrotron. And so as part of the development, we spent about a year, a huge chunk of money. I can't even tell you how many hours and days we spent at the synchrotron, but it's in the Advanced Photon Sources in Chicago. We moved our team there, so on and so on. Dr. Christian Charles and Dr. Dean Smith, who were part of my team, did an exceptional job. So we built pretty much the world's first CO2 laser heating system at this synchrotron. Man, it's like a Star Wars movie. It's like a laser on a laser on a laser. Like, think of the most elaborate thing you could think of. It's that. Built this kit out, and then the experiments begin. And here, what we're trying to do, and what we've shown in this paper, is as you compress water, it makes this very poor crystal or series of crystals. And so what we do is we compress it a little bit, we heat the water with this other laser, we take it into the melt, and then we very gently bring it back into the solidus and back up into the melt and back into the solidus, and we just modulate temperature up and down. And as a consequence, we try and grow the crystals we need. So it's like a melt quench experiment where you melt this thing and then you grow a crystal and you don't quite like it, so you take it back into the melt, and you just do this maybe, I don't know what the rep rate is, like 100,000 times in a second or in a few seconds. And as a consequence of this technique, we're able to grow delicious crystals. These are exquisite crystals. And as a consequence of this, we're able to collect very high statistical information on our sample. And so we do all this, and where do we get to? We get to the core of this paper. What we've shown in this paper is that water, which is already a very complex system, it has 18 different structural arrangements in the solid. And this is a consequence of bonding and stuff, and we can talk about that later if the listeners are even interested in this part of the chemistry. What we've shown is the main phase of water, which we call phase 7, there's up to phase 18 or 19 now, I think, I've lost count. Phase 7, which has this cubic arrangement, so the atoms are arranged in such a way that the most primitive description of this is a cube-like structure. Actually, pretty quickly is no longer cubic. It undergoes a tetragonal distortion. And it doesn't sound much to the average listener, but it is fundamental. It predominantly means that the main body of water in the interior of our Earth and on most planets is not what we think it is. And what our study shows further is, through very gentle compression, water undergoes a very unique transformation. It goes from a covalent system, where it's predominantly hydrogen bonding and the degree of covalence is increasing. It undergoes a covalent to ionic transformation. It acts like a salt. It becomes salt-like in its atomic periodicity. The way the electrons are shared are salt-like, so they're highly localized. It's an ionic form. Furthermore, there's a lot to this paper. When it goes from covalent to ionic, the bonds stiffen. It's what you call the bulk modulus, how squishy something is. And in fact, what happens is water stiffens by a factor of 2.5 at pretty modest pressures. And so all of a sudden, you have this, what was assumed to be this pretty persistent phase 7 phase no longer existing. It becomes distorted very quickly. And a consequence of that distortion, what you get is a covalent to ionic transformation in water. And this has very deep implications for the ancient water reserves in our Earth, and I could definitely build on that if you want to talk about that. We looked at a lot of the Kepler data, so I hung out with some exoplanet guys and girls, and it was remarkable listening to them. They still use data from Los Alamos database from the 1970s when they look at the pressure-volume relations or whatever for mass radio relations for their planets. I couldn't believe it. For the 90s, I was like, man, we spent millions of dollars as a community every year improving these relations, and the exoplanet community is stuck in the 70s. And so what we did is we were able to start analyzing some of the Kepler data and starting to observe that actually a lot of the planets that were assumed to just be terrestrial, so rock-like, based on our new interpretations, could actually contain a huge amount of water. So water is much stiffer than you think it is. And so when gravity tries to pull down a water-rich planet, it can't pull it as closely as you think it does. And so the radio is actually much larger for a water-rich planet than we envisioned previously. And so where they'd assumed that a lot of these planets were just too large to be water planets, actually could be water-rich planets. And so I don't know how long I've been ranting for, guys. I've just been circling in my room, talking.
Just tell us how long you have.
I've got
I'm
like
digging
I could,
everything you're
bro.
saying.
I could talk for like a month. Even my students give me a timer at work.
Okay,
I
okay.
can
Let me ask just a quick question to nerd on the chemistry a
let's hit
bit.
it. Yeah.
So no, it was a beautiful rendition of. It sounds like okay. So you've annealed these crystals into a cubic phase that's slightly tetragonal and is
Right.
ionic. And it's 3 times stiffer. Um,
Yeah. Go ahead.
so in terms of I'm curious about the pressures of those transitions and the density that
Mm-hmm.
that results in bond lengths for the ionic bonds.
There was a question at the end. Sorry, I didn't quite hear that last bit.
I'm curious about the pressures involved in the transition.
Perfect question. So, um, so you've really read that paper. So, we go from a cubic structure to a tetragonal structure, and then the ionic phase is something different. It goes back to cubic, but we'll talk about that. And so, we as a community, this high pressure community that I sit in, when we talk about pressures, we talk about pressures that are beyond any human comprehension. So we exist in the gigapascal regime. 1 gigapascal is the equivalent to about 10,000 atmosphere. And so when I talk about water in phase 7, it occurs at about 30,000 atmosphere, which no biological life that we know of so far can exist at these conditions. These are several hundred kilometers already in the interior of the Earth. The transition from phase 7 to what we call phase 7T, I've been calling it Ice-T recently, so big up Ice-T, occurs at about 5 GPa, so about 50,000 atmosphere. Again, these are, for humans, these are mind-boggling pressures, but for nature, these pressures are nothing. The interior of our Earth is just over 3 million atmospheres. The interior of Jupiter is 70 million atmospheres. The interior of our star, of our sun, is 1 billion atmospheres. Mother Nature doesn't care about organic life on Earth. She's determined this pressure extreme especially for non-organic systems. It can go very, very, very high. And so Ice-T happens, Ice-VII happens at about 5 GPa, and then the transformation to this ionic phase happens at about 30 GPa. So that's 300,000 atmosphere. Now, that sounds like a lot, but it's pretty low down in terms of the depths of the Earth. We're still talking about 600-700 kilometers into the interior of the Earth. And I can definitely talk a little bit further on that. But yeah, I hope that's a good enough answer to your question.
Yeah, great. The densities and bond lengths.
Bam. Okay, so these questions are definitely outside my pay scale. I wish I had Zach as an add-on. So density is a complicated thing for us to appreciate because let me say it like this: we probably get from ambient water, we probably get a twofold increase in density. So a good example is hydrogen. When you want to go from liquid hydrogen, so ambient pressure 20 Kelvin, to metallic hydrogen, there's a 10-fold in density. But water's already quite squishy, so we've got about a twofold in density. Bond lengths are a complicated issue. Are we talking about the covalent interaction between the degree of covalency when we induce OH bonds or when we go into the ionic phase?
Well, yeah, you mentioned we're in an ionic phase. I'm assuming hydrogen's positive, but like the hydrogen-oxygen distance.
These are great questions. So I generally can't answer this.
Okay.
I would say something between about 2 angstroms probably. The problem we have, and it's not my naivety that I'm saying I can't answer this. It's just
It's
I
good
hate
science.
speculation.
It's okay not
It's
to
good
know.
science.
It's okay not to
I'm just
know.
curious
That's what I'm
about
talking about. No, so it's a great question. So, and the reason I'm not sure what the answer to this, and if anyone says they know an answer, they're a fool, right? I mean, the reality is these X-ray techniques that I specialize in, they work on how well they scatter. So you fire a photon and it scatters when it hits an atom. The scattering power is proportional to z squared, so the number of electrons you have on the atom. Hydrogen only has 1 electron, and so these techniques that we use, the protons are invisible. We know exactly where the oxygens are, and in the paper we use a lot of we do a lot of quantum simulations that allow us to understand the protons. But the experiments we do can't see the protons. It's one of the most amazing things where we as humans, we're so bravado about our understanding of nature, but like as physicists, we struggle to even understand hydrogen. I mean, we're still fighting about fundamental properties of quarks and standard model stuff as a community. These protons are very quantum in nature. We cannot measure them, and so I wouldn't bet my house on it. But I'm going to say about 1.6 to 2 angstrom. Someone could call me out on that later.
All right, who has other questions? Because I have so many. Okay, I see no mic flashes, so I'll start with mine. First, I want to say, wow, that's really cool. Everything that you said was enlightening. Having read the paper and having worked in hydrology on Earth, I didn't know that there were 18 phases of water.
Bam, yeah.
Like, that's really cool. And being a regular in space medicine rooms and sort of, exoscience rooms, it was just really interesting to look at figure 5. I'm looking at the preprint. I wasn't able to get to the full version, but Figure 5 on the preprint, I was wondering where Earth lies on these curves.
You got to tell me which one was the figure 5 in your version. Is that
Well,
the?
it's got Trappist on the bottom and then
Oh,
Kepler.
fantastic! Oh, fantastic! Yeah, yeah. So where does Earth sit on those? It sits pretty low down. So these are predominantly super Earths where they have. So one of the limitations of Kepler is that the way what Kepler did is it points to a region of space and it takes a series of photographs. And often how we've identified the emergence of exoplanets as a whole is we see a dark blip or a shadow crossing this star. So we have a very, very bright object, and because of the resolution of the telescope, we can see a very, very small object moving across the star.
Yeah, the transit.
Exactly. Bam. You know this probably better. Yes, exactly. And so the limitation of that is we can only see pretty large objects. We often see Earth, terrestrial planets that are about 5 times larger than Earth. And so often when we talk about exoplanets, we talk about super Earths, things that are about 5 to 10 times the size of Earth. And so because they're larger and the gravitational pull is greater, I think I realized this when I was like 20 something. It was one of those like light bulb moments where, you squeeze stuff and they have different structures. And I was like, man, these super Earths, it can't have been that long ago because I don't think we were talking about but super Earths have completely different geology to the Earth. The phases in which the minerals exist in are different to that of the Earth because it's a lot
The
larger
scales
object.
are completely different.
Bam,
Yeah.
exactly. And so Earth doesn't quite sit on that because what we can only really observe is planets that are much, much larger because we don't have the necessary resolution to see such smaller planets. And so it's a little bit off that, but for the planets that we do report, the TRAPPIST ones and all the ones that I highlighted, when you think about exoplanets and super Earths, possibly everything could be different, at least within the interior, because the pressures are much, much higher, the temperatures are much, much higher. The minerals that we classify, bridgmanite, MgSO3, the various systems in the Dacomite, these things won't actually exist in abundance in these super Earths. Yeah. So I didn't quite answer your question. I kind of deviated, but it's the limitation of Kepler as a telescope that we can only observe objects much larger than that of Earth, and so it doesn't quite sit on that graph. Our mother home.
That's a great answer. I would compel you perhaps to put Earth just as a reference point for all the space nerds like myself. Even if it lies really, or maybe I don't know, maybe like a
Bro, you
footnote,
can't
like
you can't
Earth
come
would
to
be
you can't
over here.
no, bro, you can't come to my interview and critique my already published graph. But I agree. We talked
For the
we
future,
talk
for the future.
we talk about it a lot. So I mean, you're spot on. I mean, something we try to always to be honest with you, it's fascinating publishing something like this that's so fundamental in physics and it's captivated or crystallized the imagination of so many people outside of condensed matter. But it's a wonderful suggestion. I agree.
Glad,
Okay,
glad.
let me
I'm
just.
well. It was. I'm happy it was well taken. I didn't mean to
Yeah,
say anything
I'll
otherwise.
take it. I'll take that. It's a good suggestion.
Okay, no. I mean, so part of the density question was okay, factor of 2. Now, when it comes to the planet hunters,
Yes.
that's thrown their calibrations off quite a bit, right? You're saying.
Perfect question. That's a really good question. And so, exactly what we've shown is water is much more stiffens much harder than one imagine. And so, you know, the planet hunters are observing planets, and they can give us the uh, certain relationships that we can plot, right? Then once we have this body of planets that we've observed, and we know what the size is and and how they're moving around the orbiting planet, or orbiting around the main star and so on, then it's up to other members of the community to try and extrapolate data collected in laboratories and in theoretical studies and try and give us a fighting chance to understand what these planets are made of. Most recently, the techniques we've developed allow us to see the atmospheric composition of exoplanets and super Earth-like species. So we can do spectroscopy, which is mind-blowing, but light from a star can be absorbed through the atmosphere of a planet, then hits our eye as the observer here on Earth. But that's very limited. And so exactly what you're saying, we have to be able to do very precise measurements at very, very extreme conditions in the laboratory to allow our astronomer colleagues to have a fighting chance of determining what these bodies could be made up of. And in our study of water, it's really forced them to recalibrate where water-rich planets would sit. So yeah, I mean, it's a great question. It's probably the most exciting part of this work, I would say, outside the absolute fundamental quantumness of water, which as physicists we're obviously very excited about.
Okay, so forgive me if this isn't the preprint. I haven't been able to go through it all, but what since there's this potential quantum unusualness of the protons in this. What happens if you substitute with deuterons? Because in particular, the deuteron does not obey Fermi statistics; it obeys Bose statistics.
That is a killer question. I love that question. This is our follow-up study, and so perfect. So there's an isotopic. So hydrogen has three primary isotopes: protons, deuterons, and tritions. So in the case when you change the from protons to deuterons, the quantumness drops. You add the deuteron is a heavier entity, and when you substitute protons, so the lighter you are, the more quantum you are. Nothing is more quantum than hydrogen. So the question was, what happens when you take H2O and make it D2O? And so the quantumness of the system changes. It becomes less quantum, like phase boundaries move. We see the same effects. We really do see this tetragonal distortion, this Ice-VIIₜ phenomena. We also see the onset of ionic behavior, but we see it at a much, much higher pressure. And that's because what's driving this covalent ionic transformation is the quantumness of the proton. It has a huge degree of anharmonicity. So what does that mean? So you can think of a Morse potential, so an energy well, this proton's hanging out in. In the most ideal sense, the well is very uniform. It has a Gaussian-like distribution, so it's very even, like it looks like a bell shape inverted. But hydrogen, as annoying as it is, it's that bell shape is immediately destroyed. It's highly anharmonic. It's highly skewed on one side of its energy profile. And this anharmonicity, this quantumness in hydrogen drives this covalent ionic transformation of water at a much, much lower pressure than when you see it in the deuterated version. And coming back to the excellent question of what is the bond length, and I couldn't answer it because I don't know anything about science. And that's because, my argument was that X-rays don't see hydrogen. So the technique that sees hydrogens, well, specifically deuterons, is something called neutron diffraction. So instead of firing light photons, you fire neutrons. These interact with the nuclei of the materials, and they have different criteria for scattering. The community that studies water only ever looks at D2O because hydrogen has a negative absorption length and yada, 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 quantum. When you do neutron experiments, you can't see protons, you can only see deuterons. And so just orthogonal. There's been many Nobel prizes in medicine and stuff where people have crystallized deuterated versions of proteins and stuff and done neutron diffraction to look at where the deuterons sit and solve these amazing complex structures. And this is the fight we have within our community. Us hardcore physicists who appreciate the quantumness of all things are saying that H2O is very, very different from D2O. And the reason there's a big disagreement between our study and the study of the folks who look at water using neutron techniques is because they're looking at D2O. They do not see this transformation from covalent to ionic until about 100 GPa. And they're very, what's the word? Very willing to remind us about their observations. So it's a fantastic question. So you take hydrogen, you take its various isotopes, and you change them. And as you go to the heavier isotope, the quantumness of water drops. And it's clearly seen in our work, and clearly when you compare it to other people who have studied it with the deuterated system. Excellent question. Really excellent question.
Fascinating answer, so thank you.
Yeah, my pleasure.
So yeah, absolutely fascinating answer. So have you? I mean, so that's now in this quantum. Well, I'm gonna let me put that one aside. Actually, no. So the quantum nature of these protons in this lattice at extremely high pressures for us, but more or less mild pressures on a planetary scale.
Yes.
Have you been able to look into some of the other material properties of that? If these, how, what kind of quantum behavior in this proton lattice exists?
Amazing questions. Yeah. So these are just smashing questions. Yes. So water is a beast. It's so bizarre. So if you take, so let check this out. So we compress. We're at room temperature. We compress. Well, we put some liquid water in this diamond anvil cell. We compress it at 2 GPa, 20,000 atmosphere. It solidifies into phase 6. A little bit later on, it solidifies into phase 7. We've shown it tetragonally distorts. By 30 GPa, 300,000 atmosphere, it becomes ionic in phase 10. Now, if you take that ionic phase, which I'm going to label as phase 10, and you heat it, it becomes super ionic. And what that means is that it's quite a remarkable observation, and it's very unique to these light elemental molecular species like water, methane, and ammonia. The quantumness of the proton means that the oxygen lattice stays rigid, and the protons completely detach themselves and become like a soup. So you get a proton soup glooping around the oxygen lattice. And what we think is happening in the ice giants, these things that we call ice giants, are actually giant balls of super ionic water and methane and ammonia. And so the quantumness of the protons drives water to do these really, really crazy things. The big thing that Zach and I are working on, and he's going to nail it before he graduates in his PhD, or he's never going to graduate. Obviously, don't tell him that. Is there's a prediction that at 4 million atmosphere and 5,000 Kelvin, water becomes a solid liquid metal. Sorry, that didn't make any sense. Pardon me. Water becomes a liquid metallic system. Pardon me, wrong meeting. And so we're looking for this liquid metal phase of water, which potentially could explain to us what's happening in the quadrupolar magnetic fields of Neptune and so on. And so there's weird and wonderful behavior within the water construct, and it's driven by the quantumness of water. It's crazy because you assume that at high temperatures or at high pressures, the quantum nature of the quantum nature of physics dies, right? Often, as physicists, we've worked at incredibly low temperatures to observe quantum phenomena. There's been many Nobel Prizes in cooling techniques and Bose-Einstein condensation and stuff where we're in a nano Kelvin regime. But actually, as we start to explore more extreme conditions, we find that Mother Nature is actually very forgiving, and she prefers quantumness to a lot of things at extreme conditions. Yeah.
Wow.
So diamond anvils don't hold up to that temperature, do they?
They do. They absolutely. In our lab, we can go to 10,000 Kelvin.
Wow.
So yeah, put that in your pipe. That is
crazy.
some hot stuff, huh? I know.
Wow.
If anyone's traveling through
What's the
Vegas,
power draw on that? Geez, and like how long? What's the duration of that
great question. That's a great question. So again, it depends about the photon electron interaction in the material at these extreme densities, but and depending on what kind of, so we have a 200-watt ytterbium laser rod system. So this is a doped silica fiber. It's a fiber optic. It looks like a lightsaber. This thing fits in your hands. It can blow the side of a tank off.
That's so cool.
It's awesome.
Yeah, basically,
It's
I use a
ridiculous. It's ridiculous.
lightsaber. Yeah, talk about sounding like a badass. I basically use a lightsaber to do experiments in my lab.
It sounds very cool at the bar, but once people come to your lab, they're very disappointed because they're like, "Oh, cool, it's just a laser." So no, it's a laser. Laser technology has changed so much. So with a couple of 100 watts of CW light, if you set the environment and pick the correct sample, you can exceed 5,000. You can hit to about 1 eV in temperature. Now, there's other complications. How do you measure temperature that's so hot? And we specialize in optical pyrometry and dealing with emissivity problems. So getting to extreme temperatures.
What is an EV? Hold on.
It's the energy scale for temperature. You know how you can relate, everything's related in physics, right? You can go from energy to temperature to frequency to so on. Yes. So 1 EV of energy is about, I think, 11,000 Kelvin, something on that ballpark.
So 300 Kelvin is about 24 milli-electron volts.
There we go. Bam. There we go.
Oh, EV stands for electron volt. Okay.
Yeah. Pardon me. I was busting out acronyms like everyone knew what's going on. The plasma physicists. So, you know, the plasma physicists often talk about temperature in terms of energy, because to ionize something, you have to, like, you know, the hydrogen bond is 13.4 EV electron volts. And so to fully ionize it, you have to put 13.4 EVs worth of energy in. And the equivalent of that is probably like 150,000 Kelvin or something to truly ionize that system. And so, my bad.
For reference, what is the sun in these measurements?
Oh, that's a great question. So the sun is a complex entity. Its surface is only about 5,000 Kelvin only. And we can get to that temperature quite readily. It has its corona, which is very complicated. We won't talk about that. The interior of our sun, it's about, I want to say, 1 billion degrees. Someone could look that up.
Well, so
Yeah.
if we just approximate the sun's surface as 6,000 Kelvin, that's 20 times 300 Kelvin, so that's 480 milli-electron volts.
Bam. There we go. About half an EV.
So mind-blowing.
Yeah, it's crazy.
I had a follow-up question when you were talking about water turning to metal. I think that's what you said. And I was just trying to imagine water as a metal. I don't know, for some reason I just thought about mercury or something. I don't know. But how do the properties of the water change in that respect? Like, does it turn out to be something like mercury? Like, could you explain that a little bit?
Yeah.
Yeah, like what's the definition of metal at that temperature, and how can we identify it?
This is a tough crowd, huh?
Oh no.
Okay, so
I'll raise it one further. If you have the protons, you know, behaving, you know, as a distributed quantum, you know, one orbital that's highly populated, then perhaps you can have a high temperature proton superconductor.
Bam! Wow, you guys, man, I walked into a trap here. Okay, so I'm gonna.
Yeah, but you're happy. You're happy you're here. You like these questions.
I'm pumped. Okay, so these are phenomenal questions, all of them. So I'm gonna bring it back to hydrogen to make it. I'm gonna simplify this example through hydrogen, and then we'll talk about water. So I take hydrogen as a gas at ambient conditions that we breathe. I cool it down at 20 degrees Kelvin. It becomes a liquid. At 13.8 degrees Kelvin, it becomes a solid. It's a wide gap insulator, about 14 electron volts. It's huge. It looks like glass. It's totally transparent. It's covalent in nature. So the hydrogen molecules, actually, there's van der Waals interactions, but the hydrogen molecules see each other and it's all covalent-like. As I squeeze on it, I increase the degree of covalency, and I keep increasing the degree of covalency that at 5 million atmosphere, and we showed this when I was working at Isaac Silvera's group, it becomes a metal. And the metal can be assumed to just be a perfect covalent system. At high school, they're like, sea of free electrons. Yeah, sure, whatever. It's way more complicated than that. But the optimum sharing is just a perfect covalent system. And so in the case of hydrogen, you squeeze these electrons closer and closer together, and eventually they just all share evenly, and you make a metallic system. Now, hydrogen is predicted, and we will soon show, for it to be a room temperature superconductor. Superconductivity is a quantum phenomena where its principal property is that it shows zero resistance to electrical flow. When you pass electricity through a wire, it heats up, it dissipates some energy. A superconductor loses no energy. But often these only occur at very, very low temperatures. Hydrogen is shown to be a room temperature superconductor. In fact, in 2020, my group and Ranga Dias's group at Rochester, we published a paper in the front cover of Nature where we showed the first ever room temperature superconductor, although at very, very high pressures. So I've got this hydrogen, it's a superconductor, it's at room temperature, but it's at 5 million atmosphere. In the case of water, we're not quite sure what its properties will be. We're not even sure if water can exist as water itself at these extreme conditions. What if everything breaks down into its constituent elements? Like we just don't quite understand what happens in the interior of these planets. Can methane, ammonia, can these molecular species actually exist as these molecular species? Does everything then just is the real energetic minima in the global landscape, energy landscape, just the elements again? So we're not quite sure. Could it be a high temperature superconductor? Yeah, I don't know. Maybe. I mean, I don't know. What does it look like? That's a great question. It looks like a metal. It looks like a shiny metal. We showed that with hydrogen.
So this is where I was going with the question about Bose statistics, because if you could get this state with deuterons, they can exist in the same energy state.
Yes. Okay. That's true. So then we're going really deep into the quantumness of all this. The problem with a deuteronic system is that often you have to go to higher pressures to see the phenomena. And so it's a very good question. It's something we will eventually achieve as a community, as humans, but we have to go to more extreme conditions, and we can't quite get to those extreme conditions. But yeah, it's a phenomenal thing. We've been thinking about it for probably like 50 years as a community. I mean, it's a spot on question. I just want to finish my little rant by, what is a metal? It's an incredibly complicated question. I spent 3 years as a postdoc smashing my head against the wall trying to understand this. So Neville Mott, where Mott insulators come from, his definition of a metal was for a material to have a finite resistance below a certain threshold value at the limit of t equals 0. So what that really means is, as you cool things down at the limit of t equals 0, the resistance should reach a finite value which is below a certain threshold, whatever that threshold is. I'm going to blow everyone's mind right now. Silicon is a semiconductor. It is a non-metallic system. It has a band gap, whatever for you guys that might mean. When you melt silicon, it becomes a metallic liquid. So you cannot use Sir Neville Mott's analogy anymore. His analogy was, at the limit of t equals 0, there should be a finite resistance below a certain threshold value. While if you cool liquid metallic silicon down, it goes back into an insulative state. And so what is a metal? It's a very complicated question. You can think about things like plasma frequencies, so the plasmonic quantized motion of electrons and surfaces. You could think about finite resistivity, reflectivity. I mean, these become philosophical questions at these limits, because we just don't understand enough about nature.
Like, what even is a metal, man? Whoa.
Yeah, dude. That's why I have spent weeks thinking, what is a metal? It's and what is a metal? We just decided that something shiny, malleable, reasonably hard is a metal. These things are just semantics that we've imposed upon nature. They don't really mean much when you get into very, very complicated regimes of matter.
Yeah, I just want to say,
Well,
Dr.
yeah, that's why.
Dr.
So
Salamat. We asking you all these wonderful questions because we're really enjoying this presentation. It's really interesting and we're all fascinated. So we want to know more. That's what this is about. So, you're doing a great job. Just wanted to say that.
Thank you. Thank you very much.
Definitely. So, because we get to think of planets in terms of the potential of these underground lakes of superconducting metal.
Yes, I mean, Jupiter is a giant ball of liquid metallic hydrogen. You just don't know what's good. The properties are really are not understood. Um, yeah, when you look up at the night sky, it's all just so remarkable and intriguing. There's many lifetimes of research to be done.
Did you say there was a particular quadrupolar signature to the material, and does that have any way to help the planet hunters or even geologists here on Earth, probe for the larger, deposits, or not deposits, but collections of this state of water?
That's another phenomenal question. So if we're able to do magnetization measurements, but often, so absolutely, if you have quadrupolar or more complex magnetic environments, it's often near surface like dynamics, which means you have a liquidus, which most likely means you have a metallic or superionic liquidus in the system, as I've tried to hopefully convince all of you. The limitation there is magnetization measurements often require flyover. So Voyager 1 and 2 were our best attempts at getting magnetization data. So at the moment, we're limited to spectroscopic and visualization data. James Webb telescope's gone out, pardon me. We're able to collect emission spectroscopy from exoplanets using very clever techniques. And so, yes, this will be a brilliant way to get a more in-depth glimpse of what's occurring in the skin-like depths of these planets. But again, we're limited to flyovers at the moment for magnetization measurements.
Any candidates from so NASA recently announced that they had cataloged 5,000 exoplanets. Any candidates on these for Ice-VIII?
I'm already stepping way out of my field of expertise. You guys had to invite a real exoplanet specialist. I would say, let me make a remark on this. Even though our work is probably, I would say, some of the most precise measurements done on water, what I'm hoping our study has shown is that we just need more and more intricate, detailed measurements on such systems. There's still so much for us to understand. We've extrapolated quite heavily, so have others. I think the best we can bring to this table is that water is still way more complex than we ever imagined, and we just need more and more measurements. We need more improvements in our understanding. Ideally, we don't want to be extrapolating to the interiors, to the conditions we expect for super Earths. We want to be able to do direct measurements in the lab that then allow us to give us much more precise pinpoint correlations to what we're observing. I'm going to leave my mediocre answer at that.
Follow-up question, and I think the answer is probably no, but is there a potential for Ice-VIII on Earth or anywhere in our solar system?
Oh, yeah, that's a great question. And so, yes. So what's remarkable about this observation into Ice-VIII is that it goes from covalent to ionic. And where we see this boundary at 30 GPa, the equivalent is about 700 kilometers into the depths of the Earth. What occurs at that depth is that bridgmanite. So bridgmanite is the high pressure or the high density form of magnesium silicate. It is the most common mineral in the composition of our Earth. It was actually named by my colleague Oliver Schorner here at UNLV after Percy Bridgman, who won the Nobel Prize in Physics and was actually a professor at Harvard, where my mentor actually replaced him. It was a great family tree there. But bridgemanite draws water to itself at about the same pressures that we see water transform into the ionic phase 10. Bridgemanite releases water, and what we're arguing to the geology community is that this dehydration of bridgemanite, this release of water suddenly, is because water itself is going into a transformation from covalent to ionic. As it breaks the degree of covalency, its interaction with bridgemanite is finished, and the separation of rock and water is because water is undergoing this covalent to ionic transformation. And so, because we think that's happening, there must be ancient reservoirs of phase 10 water in the deep earth. This water has gone somewhere. It could have been spouted out through volcanic and seismology phenomena, but not all of it. And so there must be ancient reservoirs of water in the deep earth as a consequence of this covalent to ionic transformation from phase 70 to phase 10. And so there must be some of this in the earth. And in the case of the ice giants, we're sure there is. It probably gets very, very complicated very, very quickly, depending on where you sit on the relative depth of the planet. And so, yeah, the simple answer was yes.
Yeah, that's very interesting. I've once heard kind of one of these dogmatic like statements like there is 60 times the volume of the ocean in reservoirs within the core of the earth, and this seems to suggest that. Would you put perhaps a more precise bound on what that number might be in terms of available volume?
Absolutely not. I am not shooting. I am not. I'm not. I have no idea. I mean, I think it's unrealistic to put such bounds. Again, I think it's a foolish individual or a very brave individual to say I think X, Y, or X, Y, and Z. The likelihood is based on the measurements we've done and the measurements by the community that there must be reservoirs of water in the earth. How much? It's a very complicated process. That the earth is over 4.5 billion years old. We just don't. Personally, I don't think we understand enough about this rock that we sit on to make such bold claims. But
Yeah, I
it
thought it
must
was.
be.
Yeah, I thought it was a very odd number to have, very specific, not like 50, not 100. So I
I
was
know.
curious if there was any sort
I,
of estimate behind that, but I
I,
never got to ask the follow-up question for the person who gave the lecture. There
I
was
think,
another set of
yeah.
research that kind of talked about how the definition of metal resembles more the definition of acid in certain situations, and how their definition of metals had to change, and I forget what property it was. I guess in summary, in what way did your understanding of what a metal is change? Because I know you gave the definition, but I guess I didn't catch what was the thing that significantly changed. You
I
said you,
definitely did. I didn't give a definition. I gave a bunch of definitions by others. So, what is a metal? So, classically, you ask me what is the definition. You would say it's shiny, right? It has to be a shiny metal. It's something that you shine light on and it looks silvery. Well, actually, xenon becomes a metal under huge amounts of pressure, and it's still transparent to the human eye. But it's a metal. It has very high conductivity beyond a certain threshold. So
There's just no refractivity to it?
no, it's something called the plasma frequency. So I'm going to explain this to the general. If I get this right, everyone owes me a beer. So electrons that sit on the surface of material, their motion is quantized. They move in a very specific manner. The quantization of this motion gives rise to a quasi-particle state called the plasmon. The plasmon. So basically, these electrons are moving. If you're, and they have a frequency to them, right? If you're a ray of light, you have a frequency to you. If this ray of light wants to make it through this material, the frequency of the light has to be faster than the frequency at which these electrons are breathing. And so, for
And
example,
perhaps the frequency that, I mean, I guess we're not only talking about just the human eye without any augmentation in terms of
we're
observation.
gonna forget the human eye for a second. So, for example, X-rays. the reason X-rays make it through most materials, in a very, very simple understanding, is that they're very, very high energy, and so they have very, very high frequency. And so this frequency is much, much higher than the frequency at which the electrons on the surface of this material are moving. And so it can make it through. If the frequency is lower than the frequency of these electrons that's moving, it bounces off the electrons. And so that's why nearly all materials are transparent to X-rays. Now, with metals, the plasma frequency is somewhere in the deep UV. And so once you go into the UV regime of light, metals are opaque. They are no longer transparent. A non-metallic system like glass is still even visible in the visible light. And so we as physicists, when we talk about metals and non-metals, we're actually talking about it on a very deep level of plasma frequencies and the quantized motion of electrons on surfaces. That's why we've been pigeonholed into this very obscure understanding of metals, because everything else doesn't quite work. So we're sitting in this very niche area of trying to talk about plasma frequencies and what does that mean and what is the threshold and stuff. And so when I think about metals, I think about it in a very weird way. I don't really think about it in terms of like, is it shiny? I don't even think about conductivity really, because so on and so on. So yeah, I hope that answer was helpful.
Okay, thank you. Yeah, I appreciate
Yeah,
that.
so it's like some rants. Yeah, cool. So yeah, it's very complicated. It's very, very complicated. And the deeper you look, the more. If you're not amazed every day, you're doing it wrong, really.
It's really
So I hadn't thought of metal surfaces in terms of just their reflectivity in terms
Yeah,
of surface plasmons. Is this kind of like the magic situation where you have the electric field and the magnetic field of a photon kind of getting a surface plasmon to zip around in just the way that it shakes it back off at the
bam.
opposite angle to the normal?
Exact. Yes. Pretty. Simply put, yes. It's this phenomenon. So it's the transwaves form of the photon. You have the magnetic and electric component. It's the electric component that interacts with the electric field of the electrons on the surface. And so we often think about it like this because, like the example I gave was xenon. Xenon is a metal under 1 million atmosphere of pressure, but it's transparent because its plasma frequency sits in the near IR. Where metals, it sits in the UV, and so they're opaque. Anything above the UV, xenon's plasma frequency sits in the near IR, and so it's only opaque above the near IR, so above 1 micron wavelength, and so it looks transparent to the eye, even though it's a metal.
Given that humans have 3 or 4 cones, now you have me wondering how a shrimp looks at it, like with 12 cones.
Man, I got a high one in my lab because I bet those suckers could spot a metal from a mile away. Yeah.
yeah.
Yeah,
Mantis
so
shrimp has a color vision of 12 degree.
wow,
Yeah.
that'd be good
They also have the ability
methodology.
to, I guess, see polarized light, circularly polarized light, which is pretty cool. Was there any circular polarization component to this? Because I know you just mentioned kind of the different waves, but is there any component of that, or perhaps that's future research?
It's a great question. And so these diamond anvil cells, when we compress materials, the strain tensor along the diamond is non-uniform, and as a consequence of that, it disrupts all polarization of light, and so we get scrambled light out of our measurements, and so we're not able to do polarized measurements coming out of a diamond anvil cell. And we've been thinking about this. I think there's tricks in atomic, molecular, and optics physics that we've been thinking about, but this is a limitation when it comes to optical techniques in the diamond anvil cell, is that we can't do polarized measurements, visible polarized measurements. Now, there's obviously other photons of higher energy where you can polarize those photons.
I have a question on it. Yeah, thanks for Dr. Salamat. It's fascinating that how you explain science so well. So about the end itself, can you? I'm curious about the size of your sample that in preparation. What is
Yeah,
how many? Yeah, what is the amount?
fantastic
Yeah.
question. Absolutely fantastic question. So this is bringing it right back to the fundamentals of the technique. And so the diamond anvil cell has two pairs of diamonds, gem quality. And unlike your diamond ring, if you're blinging it out, the diamond ring often has the table, the back end of the diamond showing. If you take that diamond out and turn it up and on its bottom end, looking up, it looks a bit like a pyramid. And what we do is we use the very tip of that diamond to do our measurements. Now, very simply put, pressure is force over area. And what we do is we take a modest force and we divide it by a tiny area. And as a consequence, we could get to huge, huge pressures. So there's an inverse relationship between area and pressure. To go to 5 million atmosphere for hydrogen, your sample sizes are in the order of a few microns. So somewhere between a tenth to a hundredth the width of a human hair. For these water measurements, the pressures are much more modest. We're only going to like a million atmosphere, for example. Sample sizes are about, I'm trying to think back on a good day, 100 microns in diameter, a couple of microns thick. So they're pretty schnuggly, they're pretty small.
What about the time element of the experiment?
Oh, brilliant question. So a diamond anvil cell environment allows you to have a static setup, which means you can indefinitely hold a material there for the lifetime of the material, the lifetime of diamond, which is about 1 billion years. These are static measurements, and so the timescales are very, very long. The counterpart to our community are the shock community. So we do
Geological timescales,
yeah,
potentially.
yeah. Of course. That's a great.
The
Yeah.
so for the water for the H2O is so under such extreme conditions that you're applying what the role of the oxygen atoms are playing. I mean, is it more important than the hydrogen, or is it
Oh,
because
phenomenal.
it's metallized as well, right?
Well done. Exceptional question. So oxygen on its own at at 96 GPa, so just below a million atmosphere, it becomes a metal. So oxygen, you can make metallic oxygen. It's going to be the future of rocket fuel along with metallic hydrogen. I'm sure, you can have these remarkable high energy fuels. The role of oxygen, well, if you take oxygen has to be there for it. Oxygen and hydrogen have to be there for it to be water. If you change any of the constituent elements, it's no longer water. So I can swap oxygen for nitrogen and make ammonia, NH3. I can take oxygen and swap it out for carbon. I can make methane, CH4. So compositionally, the material is defined by its constituent elements. So it's not like you can change them in and out. If you do, you just make another material. Its role is predominantly plastic-like. It provides a very rigid body to which the protons can do all their weird quantumness. It's still quite light in its atomic mass, so it can participate within the Born-Oppenheimer approximation. But yeah, I mean, to be honest, all we ever measure is the damn oxygen. I wish we had a better portal into understanding what our quantum friend protons are doing.
Have you all been able to look at effective, small impurities? Like you throw some lithium in there or whatever.
Oh, fantastic question. Absolutely fantastic question. We have not. We are purists, so we are hardcore physicists trying to understand quantum nature and trying to overplay our hand by understanding the universe at the same time. Our geology colleagues have done a phenomenal amount of work. From a geological standpoint, especially understanding the Jovian moons, they've been looking at a lot of salty water. So we know a lot of the Jovian moons that do have water are highly saline. I don't know what salinity content. for ourselves, we try to look at various mixtures. The problem is, well, it's not a problem. I'm fascinated by metrology. So metrology is the art of the measurement. You know, I have taught my group and my center we want to be the world's, one of the leading groups in the world in doing the most precise measurements. And to do that often, you have to have very simple systems to look at. So it's just water. Like I'm still confused every day when I wake up and I think about water. The thought of adding a contaminant in there, I don't think my OCD levels will allow it. But these are perfect questions for others to go away and do. You know, what happens when you add metals in there? What happens? I mean, a great question is, for example, do any of the ice giants actually have rocky interiors? Do silicate rocks, are they insoluble or soluble in a super ionic liquid? So if you make a super ionic water state, does the silicate just melt or dissolve into it? And if it does, then none of these giants in our solar system actually have rocky interiors. So
How hard would it be to perform that experiment?
In my lab, like I always say, one day, and like 4 years later, we still haven't done it. We specialize in my group. We specialize in these techniques. We have a lot of questions to flurry through and get through, but nothing's easy, right? If you want to do something right, the beautiful thing about science and understanding Mother Nature is, no matter how simple the question you have, once you start to dig, you realize the trench you're digging is endless.
It's turtles all the way down.
Oh, it's the worst. And what makes you a successful scientist is knowing when to stop digging. That's really all it is. You either dig.
There will always be more questions.
Well, there's always
for sure.
more work for grad students, right? It's turtles all the way down, as my quantum prof said. So sometimes you want to have to keep.
I'm worried some of my grad students are on this line, so I'm not going to make too many grad student jokes. But yes, you're right.
Yes, to be a scientist and to be sane at the same time. Yeah, excellent. And so, by the way,
mad scientist.
I got very, yeah, exactly. I got very, I learned a lot from it. Thank you so much. So you mentioned something. So I'm just trying to draw the picture. I mean, getting a take home like a message that the water, the H2O, when it becomes metal, is mostly you said that is the quantum behavior of the proton, the hydrogen. And it's electron that's being shared, converted from covalent to the metal. Shared. Is that the right
Amazing question.
picture?
Amazing question. And so I'm going to bring it back to just hydrogen again, just to blow everyone's mind. So metallic hydrogen, right? Hydrogen, each atom of hydrogen only has one electron. This electron, so I form a periodic lattice with my hydrogen neighbors, my brothers and sisters left and right of me, up and down of me, and we all hold hands. And we form this rigid network. And every time I hold a hand with my nearest neighbor, I have to give an electron, it's a 1s bond, and they have to give another electron. So we have to fulfill 2 electrons for this Hund's law. Then where is my electron now in participating in the conduction band in being a metal? If I'm only a 1 electron system, how can I form a bond and also contribute electrons to the conduction band to behave like metals and be free carriers and do all the things a metal is expected to do? And so this was one of these, deep philosophical questions we kept asking ourselves as postdocs. I mean, we had the best lunches. We just had the best, no one would eat. Everyone would sit there in silence and just think about these. So what happens in hydrogen? You have to form a bond and still contribute to the conduction band. And so we think the most rational answer, that's not even rational, the easy way out of answering this is that in the case of hydrogen, the electron participates in both functions. It's quantum. It can spend some of its time in bonding and some of its time in the conduction band, being a free carrier. How this tau, this temporal contribution occurs, I'm just making it up, I have no idea, but there must be some, I don't want to say superposition, but this ability for the electron to perform both functions. Otherwise, how can a one electron system be a metal and still form bonding and still do all the things? And so, yeah, it's an exceptional question. When it comes to water, I think it's a little bit easier. Oxygen has much more electrons. It has its lone pairs. It can participate and provide electron density. The partial density of states, when you look at the electron band structure, if that means anything to anyone on this call, can be rather more convoluted. But yeah, things get difficult very, very, very quickly.
So this seems like a problem that is like natural to treat with configuration interaction, and since you're dealing with one proton, one electron, presumably that's the unit cell, or maybe there are 2 or 3 or even 6, but this is something that can be done explicitly with full configuration interaction in a periodic system. So I mean, this seems like a really interesting computation or quantum chemistry problem that's really tractable.
Sure. So my group is divided into experiment and theory. We have a very active theory component run by Dr. Keith Lawler. Okay, so the problem with these so if we're stuck in the world of density functional theory, the choice of functional is so critical in capturing these behaviors and dispersion effects in molecular species. And I don't want to rant. I could rant about this whole thing for another week. Makes it very, very challenging within a molecular dynamics or some kind of Monte Carlo simulation. It's probably the way to solve these things, but the limitation there is we cannot tell the theorists what the true crystal structure of metallic hydrogen or metallic water is. We cannot tell them, we cannot provide them with enough quantifiable evidence for them not to just be looking into, like, they're just looking out into deep space. Yeah. Well, I'm sure they're taking it very, very seriously, but whether we are taking their results seriously is a different issue, because as experimentalists, we provide anchor points. We rely so much on theory to help us explore this vast phase space, but we provide them anchor points, and they often go back and come back and revise their calculations to see if they come close to the anchor points we provided. And whether this Ouroboros or this feedback loop mechanism for these very unique states of matter that we've talked about, there's very limited experimental evidence, and so it's very hard for the theorists to go away. What crazy assistant professor is going to blow their tenure track promotion on some damn silly question about water when no one's going to believe their answer?
You need to find somebody with tenure already. But,
I know, that is a spot on.
But
absolutely.
One comment, I really doubt that density functional theory would be useful, because they all have empirical parameters that are derived from totally irrelevant situations. That is, or ordinary conditions, right?
Absolutely.
But something like a free electron gas approximation.
Yeah, but so yeah, for sure. So, like, let me give you another example. Like hydrogen, it's very hard to. We haven't measured or yet computed the 0-point contribution in hydrogen, which is prominent. And so even when you even look at hydrogen, you can't even account for the 0-point motion. And so this is fudge. This is a fudge factor that theorists put in. So now we can do, quantum Monte Carlo simulations that are then fed into the DFT and yada, yada, yada. But even the 0-point contribution at a tenfold density has never been measured and can only be guessed of what it is. And so
insert assumption here.
There you go. Exactly. And so, and then the theorists will fight for the next 10 years because one group thinks it's this and the one thing, but we still have to just appreciate the complexity of nature and just marvel in her amazingness, and just what it really means is we just don't have enough information. It doesn't mean other groups shouldn't be working on these problems. All we can do is just keep bashing away at the block of knowledge and hope that one of us gets a big chunk out of it at some point.
It's only a matter of time.
So yeah, the theory approach, I mean, we'll get there eventually, and I'm excited to be part of that gang if I'm able to do so.
Well, it's humbling to think that in that you can't tell the theoreticians enough to even set up the full CRAP calculation.
Not even on hydrogen. I mean, theorists prefer very heavy, well, not too heavy because then F electrons revolve, but they're like mid periodic table elements. You know, some classic stuff. Throw in a couple of vanilla PBE functionals. But the second you go to the very, very light elements or the very, very, very heavy elements, then it's very, very hard to capture the nature of that system.
Hello,
Just
Doctor.
quickly. Sorry. Go ahead.
You go first. You go first. Sorry, you go first.
Okay. Just a quick question. So you mentioned the shape of the crystal structure of the water 10. I forgot what you say. It's cubic, is it?
It's cubic. It goes back to cubic remarkably, yeah.
I see. And then you said you mentioned the shrinkage is about a factor of 2, the volume.
Yeah, 2.5. The compressibility.
The compressibility.
Yeah, I didn't quite say. I said the bond stiffness. I gave a very generic term there, but the really we're looking at the bulk compressibility, the bulk moduli. But yeah, the bond stiffens by about 2.5. But yeah, go ahead.
Yeah, I was just trying to draw the structure and where the hydrogen and the oxygens are, and trying to see in the cubic type of relative position. Then okay, so I'm trying to see. I mean, what if you start with oxygen and start adding more protons to it? I was just wondering.
Great question. So I'm going to help you with your visualization of your model. So phase 7, even phase 7T, which we've reported, there is a disordered phase of water. There's a proton that sits between 2 oxygen atoms, but this proton has a double well, has a double energy well. So it can exist in either one well or the other. And so when you classically draw it out, it looks like there's 2 protons, or the proton exists in 2 different positions between these 2 adjacent oxygen atoms. As you squeeze the material and you get to phase 10, this ionic phase, these 2 wells get pushed and mushed into each other, and it forms a single well. And so by the time you get to phase 10, there is a single unique position for the proton to reside in between the 2 adjacent, or the 2 oxygens it sits in. And so I don't know if that helped your analogy, but again, it's a very I think about
A
it in terms
reference
of
will be lovely. Yeah, thank you. It's very animated.
Yeah, cool.
When you mentioned oh, sorry, go ahead.
Yeah, sorry, can I just ask, Doctor, that sounds fascinating. I'm sorry, I came in a bit late, so I'm going to have to hear like the first major part of your talk on the replay. But when I came in, I heard you mentioning about the electrons, and you know, using with the hydrogen atoms and stuff, and you said about them all holding hands and being like in a lattice work and everything. When you mentioned about them, like how do you have it behave like a metal, but it's only got one electron, and they seem to have like, or they could have like dual purpose, like a single electron, like doing 2 things to make hydrogen a metal as well. Now, please forgive me for being totally stupid, or you've totally covered this,
Not
but
at all.
Is that that sounds like that kind of mind blowing. If an electron can have a dual purpose to make a kind of like 2 properties to like one thing or something, is that something that exists
It's
already,
all
or
quantum,
are we?
baby.
Yeah,
All
so
quantum, yeah.
are we literally talking about something that can blow the mind out of like chemistry and physics as we know it? If we know that all the things that we hold to have like one state or of being, it turns out they can they have night shift to something else.
I could give you. It's a very good question. It's a very solid question. I'm going to give you an analogy. I play a lot of pool. My fellow Scotsman here probably plays a lot of snooker, hopefully back in the day. But when you play pool, you have a white ball. You see the balls ahead of you. You apply Newtonian mechanics, and you pot ideally the ball of choice. If I was going to play quantum pool, then all the balls will already exist in all the pockets all at the same time, And it's only when I choose to see a ball of choice does that ball then materialize, and I could potentially put it in the pocket of choice. But on an atomistic level, the universe is statistical. And so when we talk about an electron has multiple purpose, it's because statistically it can exist, be doing one purpose or one function, has one spatial coordinate, has one distribution, one probability of existence. But because it's statistical, it's not 100%. It can also be doing something else, or exist somewhere else, or be somewhere else, and so on. And so, and it's mind blowing. I don't know if it's Feynman. I guess Feynman's associated with, but if you think you understand quantum mechanics, then you truly don't understand it. It's this very weird, bizarre world, and so this dual purpose of the electron is not bizarre in the quantum realm. Many things do it. What makes it difficult to comprehend for someone like myself is this idea of a metallic hydrogen framework with nothing else participating in either the bonding or the conductivity or the other phenomena. And this poor electron's doing a lot of work. I hope it's getting paid above minimum wage, because it's grinding it out on multiple fronts here. Yeah, so I hope that helped answer your question.
Is
No,
that
those
just
are
is that
the suckers that don't get anything. The ones that actually
Oh,
work.
they're not even getting. I hope that, because they're not unionized. They need to get unionized and lead from the front.
Well,
is that solid quantum theory that they can have joules, or is this like just speculation at this point, or is this like established that they can do that, or at least they seem to be able to have dual purposes like that? Because I'm finding that's breaking my head open. That it's like everything we know about everything is not what we know, not really correct.
Yes, I mean it's pretty well. These are measurable effects. The statistical nature of quantum mechanics is a highly measurable phenomenon in the laboratory. I'm going to go off the book. I've been watching a lot of Star Trek Discovery, and so I've been really thoroughly
Hell
enjoying.
yeah.
I've
Hell
been
yeah.
really
Beam
Hell
me
thoroughly.
up.
yeah.
Oh, damn right, damn right. I've been thoroughly enjoying mainstream TV shows. I mean, Star Trek's phenomenal, but
I'm
really,
rewatching
really
Deep
picking up.
Space Nine right now.
Damn right. I finished Voyager like 2 months ago, but in Discovery they play a little bit about multiverse theory and all this stuff, and actually it becomes, the thing is, it's outside this discussion. It becomes metaphysical. It becomes into the realm of philosophy. We're beyond the measurable now. It's not something I like to often talk about because I'm a geeky experimental physicist. Anyway, yeah.
Thank you very much,
Strange New
Doctor.
Worlds. Strange New Worlds, right here. Deep fake
Yeah.
myself over the captain. So hell yeah.
so what's particularly strange and occurs to me, and this can be both in the case of um, not metallic hydrogen but metallic deuterium, and also the case for water, I guess, at super high temperatures. The notion here is that the electrons, being fermions, obey Fermi
Mm-hmm.
statistics. But when you have nuclei that are bosons, right, and
Mm-hmm.
can number one occupy the same energy state degenerately, right?
Yep.
This is like a fascinating question for how you would calculate that, in terms of what happens with regard to exchange, right? Because now you have what you would ordinarily think of as the nuclei forming the lattice, right? But they are identical, so their interchange would be handled differently under exchange, kind of the way electrons have to be, treated. You have to, include that term in the wave function, right?
Can
Do you see where I'm
what is your
going?
what? Absolutely. What is your background? Are you a professor of
Well,
physics?
I actually don't even have a doctorate. I
Oh,
I
where you busting out these questions from?
I have been doing quantum chemistry for the purpose of calculations on positional mechanosynthesis and nanofabrication,
Oh, cool. Oh, I've done.
Drexlerian sort of stuff.
Oh, excellent. Yeah. All right. It's a super deep question. So let me try and sum it down for everyone. So just for the general audience, the spin integral, fermions have a half, bosons have one, and it's basically, it allows us to divide the whole of all matter into two subgroups, and they have very different properties. The Dirac Fermi statistics describes things like electrons, and Einstein statistics describes the boson stuff. So it's a phenomenal question. I'm not going to answer it because I don't really have a good enough answer for it. I've been yapping for about an hour and a half. I think I've run out of juice, but that's the kind of questions we're interested in as a group, because even in nucleation processes, there is a difference between how deuterated water and hydrogenated water behave. Even in the macroscopic behavior of water, there is some underlying quantum phenomena that drives macro behavior, and it's just remarkable. Often, because of the de Broglie wavelength and stuff, quantum phenomena is often sort of very small, atomistic. Once you get into the macroscopic realm, the quantumness of materials diminishes, it dies. But in things like water, growing of crystals it's a very clear macroscopic phenomena that you can observe. And when you deuterate water, it grows quite differently to how the underdeuterated version works. And so it's a great question. It's something we've been really deeply thinking about. It's a deep physics question. Yeah, I'm going to leave it at that.
Understanding this conversation is slated to go to a geological timescale. But given that you are a human, how much longer do we have the honor of your presence?
I have one more question. I think it's a cool question. So
I don't know. Are you guys still pumped?
yes, I am super pumped.
Geological timescales, man. We're ready to go.
Yeah. Okay.
I just want to say, if my sister's listening to this downstairs, I'd love someone to bring me up another whiskey. But keep going.
On the way.
Okay, I have a question. So Lee Cronin did this kind of I guess popular science video for one of those channels, and he talked about how potentially there could be organisms or metabolisms at some of these higher pressures and temperatures where the organisms might use magnetic fields because they would have some sort of perhaps exotic interaction at those temperatures that may give rise to something analogous to what we call life. Could you or do you speculate about that?
Sure. Lee Cronin, is he the chap at Glasgow by any chance? Oh, yeah, I know him. Watch him speculating about life on Earth. Okay, so in my field of high pressure physics or high pressure sciences, there is the high pressure bio community, and they've done some phenomenal work in trying to appreciate the effects of pressure on life. It originates from actually the food industry, where, similar to pasteurizing, one of the main methods for cleaning food is they put them in these very large rooms with the ability to go to pretty high pressures of several thousand bar, I would say, to kill bacteria and other unwanted things. The deep life component of extreme science has been looking at the Mariana Trench and understanding the evolution of life here on the Earth. And it's often speculated, at least within that community, that the presence of life on this planet could have come from a dynamic high pressure interaction. And what I mean by dynamic is, unlike my experiments, which are static and geologically slow and can be contained, a meteorite hitting the Earth, for example, can drive the pressure temperature scale quite uniquely. In fact, very unique for that interaction. And although the pressure and temperature can be very, very extreme from a meteorite collision, on the tail end, when it dissipates, there can be unique PT environments that could have given rise to complex life. So clay pools with RNA and so on, which can then get driven to pseudo DNA. I'm not a biologist, right? I'm just speculating. These are like pop science books I've read.
Yeah, I've actually pinned the video to the top, so perhaps for a future discussion, or even just for your entertainment purposes and everyone else, please do check out the video. My mother saw it, and one day she heard me talking to Lee Cronin because he comes on the app was coming on here regularly until a while ago. and he was talking about these topics. And so, just by sheer coincidence of his unique
Oh
voice,
yeah,
I got to learn about this video, which my mom found, and it was quite interesting, at least in terms of the visuals. And so, when I asked him, he kind of said, "Oh yeah, that's just something that I did." And so I was curious because your work is a lot more
yeah.
in that direction, but of course the
So
biology might be significantly
yeah,
different.
just to say, so the way Lee Cronin knows any of this is that my PhD supervisor, Paul McMillan, who unfortunately just passed away last month, he was the professor at University College London. Towards the end of his career, he specialized in this problem of of extremophiles, they call them, and understanding the origins of life through pressure temperature perturbations. So if just Paul F. McMillan, if anyone can come across his papers, he's done some amazing work on this. I'm not an expert, but it seems that extremophiles, so biological systems that can exist in very extreme conditions, whether it be like the hot springs in Yellowstone versus the Mariana Trench, could be providing us glimpses of information which will allow us to understand the origins of life, which could most likely come from some weird meteorite impact.
So two things that differ in these kinds of conditions that we've been talking about, that compared to even what the conditions that these extremophiles exist in are, the lack of at least the same weak bonding interactions, like the hydrogen bonds that hold DNA together. Those would not obtain at all at these conditions, unless maybe
Mm-hmm.
the Bose statistics can come into play with something analogous but totally different. But then also, it's unclear to me that there is even stable valency. Would you say that there is stable valency?
At the most extreme conditions.
Yeah.
Yeah. So I talk about this a lot with my students. So classical chemistry, valency, coordination number, oxidation states, these mean nothing under extreme conditions. The
That's what
periodic
I
table,
thought.
yeah, it's very annoying, but also very exciting. The periodic table itself takes a different shape at various densities relative to the elements of interest. Um, it's a very bizarre world. As you compress materials, let me give you some beautiful examples. Sodium, which we all know it to be an alkali metal, it's highly reactive. When you compress it above 2 million atmosphere, it becomes a transparent insulator. It goes non-metallic. You can squeeze metals into non-metallic states. In fact, sodium does a very unique thing. It forms something called an electride. Its electron density separates away from the nucleus and forms gloops of electrons stacked in interstitial sites inside the sodium framework. So with pressure, you can drive metals to non-metallic states. You can drive non-metals to metallic states. Coordination, valency, all this just goes out the window. It's
Wow.
absolutely remarkable. It's mind
I'm
Yeah,
blowing.
not going to be
that's
able to put salt on
wild.
my fish and chips again. Think of salt the
Yeah,
same
there you
way
go.
now.
Yes. So it's just staggering. It's just staggering. For me, it's actually staggering how naive as humans we think this whole construct is built around us, and really we're just glimpsing into just a set of conditions at a certain time and trying to make the best we can of it. It could be very, very different for other systems or life or whatever on very extreme environments relative to us.
You simple humans. Oh.
Yeah.
Ash, did you just use the word interstitial when you were talking about these
Yes.
clumping?
Yes, I did. Yes. Would
Okay.
you like me to expand on that?
Yes, please.
Absolutely. And so when you have a periodic arrangement of atoms, you know, uh, nature is very, very complex, but actually the way she makes materials or compounds is
predictable if we can see the entirety of the pattern. We
bam,
just haven't
bam,
gotten
bam.
there yet.
Exactly. We use a series of mathematical constructs to summarize nature. We use something called space groups. These are symmetry operators. We have 230 unique space groups that describe all of three-dimensional nature. Now, it's probably not true, but we have summarized often as humans, since we rely on pattern recognition to allow us to take a very, very complicated environment and minimize it into these palatable shapes that we as mere humans understand. So within these constructs, an interstitial site is often when you have atoms periodically arranged, you can stuff things between two atoms. And so that's when we often mean interstitial sites, where you could stuff this thing between these two I don't want to get too technical because then we have to talk about other stuff. But yeah, it's the stuffing of things between other things in a periodic arrangement. That's probably the worst description ever, but
And so when you think about this at the really high temperatures where the thermal energy expressed as electron volts might be higher than the de Broglie wavelength of the atom, less its valence electron. I really wonder about whether you'd have anything analogous to Fermi smearing of the atoms from one lattice site to another so that they could exchange.
yeah, another great question. And so okay, so I'm going to bring it back to hydrogen. This is a general audience, and I don't want to complicate things. So hydrogen is a great thing. One way you can think about, I talked about what's that electron doing? Is it sharing with its neighbor? Is it in the conduction, participating in conductivity and stuff? One other way to think about it is the wave function that describes a proton, a hydrogen atom, is the wave function squared, tells you the probability distribution, and the whole information about this proton, this particle, is contained within the wave function. When I squeeze hydrogen, what you can imagine is you have these series of atoms or molecules. It starts off with molecules, but maybe it dissociates into atoms, and each one has a wave function. And as you squeeze them closer and closer, the tail ends of the wave function start to smear out and start to overlap. And a pictorial explanation for yourself could be that the smearing of these electrons, of these wave functions, as they overlap, is what actually leads to this final metallic state, where now you have a continuous spreading of these wave functions in that sense. I don't know if that was a good answer, but yeah, we think a lot about all this stuff.
I mean, I just like I so want to tie this back to like the delocalization of electrons in benzene, but rather for the nuclei and lattice sites.
Yeah, so actually, I could. That's again a great way to think about it. So the amazing one, if you want to take that example to the absolute extreme, is this electride that I mentioned, this sodium electride. Sodium becomes transparent, and what happens is the electrons actually rip themselves away from the nucleus, and they sit in these balls together. Sorry, someone's bringing me a drink and being very rude about it. So these electrons separate themselves from the nucleus, and they punch up in these blobs and sit in these interstitial sites. So you actually get complete separation of electrons away from nuclei, which is mind blowing, because the effective nuclear charge often is what pulls the electrons and keeps them in their orbitals. And yet, through density perturbation, the electrons are like, forget this. I can completely lower the free energy of the system by actually completely separating from the nucleus and going to sit in some random site, far away. And so there's all this weird and wonderful phenomena, yeah.
I'm my head is swirling about this material, the Ice-VIII, and the properties that it might have. Is there humor me. Is there any practical system that we could actually make a sample and trap it and wire it up and study it in a sense that, or is that 30,000 atmospheres just beside all warnings of contents under pressure and that sort of thing? Is there a way to trap that?
You're being generous. It was 300,000 atmosphere of pressure. I wish it was 30 in the sense. So it is trapped. It is trapped inside of a diamond anvil cell.
Right.
So it's not like you can touch it. It's still confined in this environment. For more modest pressures of maybe tens of thousands of atmosphere, there are now lots of tricks within chemistry that allows you to print materials on frustrated lattices. It's a very complex. We can talk about this endlessly, but you can print materials on frustrated lattices where they feel a pressure equivalent of up to 50,000 atmosphere. So that's still far away from Ice-VIII, but there are techniques which we can manipulate nature to allow us to get the equivalence of pressure in there. In terms of water and phase 10, it probably has no real functionality for life or humans. It's a very fundamental thing, and it's completely necessary for us for understanding planets, our environment, exoplanets, and ice giants, and so on. I don't know. Maybe it makes an amazing drink, but I'm not. I don't know. Maybe aliens drink it in there. Maybe aliens have Ice-10 ice cubes or something. I have no idea.
Ban Galactic Gargle Blaster, one of them. Yeah.
There you go. Yeah.
If that's not a drink already, you just gave away some IP.
Yes, I know. Well, really quickly, we've been making one of the things we can do is we can make CO2 into a glass. So you can compress CO2 gas and make it into a glass. Actually, we mix it with SiO2, which is the main constituent for normal glass. So you can make SiO2 CO2 glass. And one of the big things we were thinking about was self-carbonating bottles, where you can pour water into your bottle, and the CO2 from the glass would then diffuse into the water. There we go.
That's incredible.
Wow,
That's awesome.
self-regenerating bubbles.
May
Yes,
I ask? I guess we kind of touched upon it here briefly for a moment, but I guess one of the things that labs have to do is sometimes generate revenue for universities through research, through grants.
Yeah.
Can you comment a little bit on your perception or how you feel about IP or intellectual property and how that helps or doesn't help science?
Yeah, that's a great question. So I can tell you a bit about my journey. I actually have a startup with my co-founder Ranga Diaz. It's called Unearthly Materials. We specialize in quantum materials. We raise a lot of capital through VC firms, which we then pump into our research group. And the reason for that is, I don't want to burst everyone's bubble here, but I worked really damn hard to be a professor. And once I got here, I was a bit disappointed because it's not like I could go away and work on any problem I want to work on. There are funding agencies and bodies where they define their mission goals for the next 3 to 5 years. Actually, all this work on water, it's not funded by anyone. I've had to fund it through other means. No one's been willing to give us money for this work on water. It doesn't resonate with NASA. NASA's been thinking about the James Webb and has all this other thing. And so you get to this academic point in your career, and you're like, bam, I can work on anything. And the realization kicks in that funding agencies actually have very rigid frameworks, and they have their own perceived ideas of what's important for the funding agency. And so it makes blue sky research like this incredibly challenging. We've been lucky. We've gone off and done other things that has generated funding for my group and for my center, and we've developed IP that's allowed us to get money from VC firms to then pump back into fundamental science. And so maybe the noble thing from the English lords and gentlemen of the 18th century would tell you that fundamental science is pure and so on, but in reality,
not if it's not funded purely.
Yeah. So great societal change often doesn't come from academia anymore, and so the world is changing. Academia is changing. You know, our incentives for driving to IP and generating external revenue is to drive our fundamental science program within our academic institutes. So, yeah, I think naive me would have said, "Oh man, that's not what scientists do, and you should just do science, man, and like just get money, bro." In reality, running a 20-person group like I do, I need, millions of dollars every year running from my group. I've got to pay salaries. I've got to break lasers. We break a pair of diamonds every time we do an experiment.
Could you tell us what it takes to run one of your efforts on an annual basis?
Yeah, you got to bench like 275. No, that's a private joke. I have. I mean, let's be honest. I have 7 active grants. And I work in a state school. We're an EPSCoR state. I have worked incredibly hard. Have an amazing group of people around me, and have dedicated my life for this. And that's what it takes. Now, if you don't have access to that kind of funding, you cannot do some of the things we've done. So, as I said, this whole water project is funded by ourselves. I have begged, borrowed, and stolen. Well, it's not stolen, but to get capital to do this problem, because Zach and I are passionate about understanding how these damn planets work. But our real money in my group comes from superconductivity research, from high energy density materials, from
things that
building.
commerce are interested in.
Exactly. That's what's so upset. Spot on. People, if you can make a device, people will throw money at you. But if you care about how the interior of some planet works, or whether there's ancient reservoirs of water in the Earth, no one's going to give you a buck.
I'm surprised
Like,
NASA's not
no.
interested in
but
working with you. That's
yeah,
surprising.
My proposal's been rejected. I mean, I'm not going to call NASA out, but whoever we submit it to, our proposal's been rejected 4 times. It's too.
Well, so listen, Dr. Jim Green, chief scientist emeritus now as of the beginning of this year of NASA, frequently comes on the app, and I think he would be
Great.
fascinated by some
He
of
has
the things
great
you're
rooms,
talking.
Yeah.
Talking about that, and of course it won't get you funding right away, but he has remarked how many good proposals have been rejected 3-4 times, but then they get funded.
Yeah, that's the thing that I also complained to
Quick.
him about personally, and he was like, "Well, if it didn't come to my desk," and I was like, "Yeah, well, I guess there's a lot of people. It's a huge machine,
There's a lot
but
of
this is something
desks.
that scientists
Yeah,
feel."
I
Yeah,
like
yeah,
I get
and
all this. I get all this, and like 4 or 5 times. Okay, so
What is
I
this,
think
an
what
insurance company with you're trying to make a claim
yeah,
against your
exactly.
policy?
I think the reality is, look, as junior academics, I go to a modest state school. I've done pretty well, but if you're at a higher school, your tenure track process is incredibly competitive. You cannot wait 4 or 5 times to get a $400,000 federal grant where 50% goes to overhead, if not more, where you could probably pay for 2 grad students max, couple of diamonds, and break a laser. If there's a need in this country for fundamental science and like this, it cannot be a 4 or 5 time review process. There are other avenues of money which I've explored, and they're easier to access, and we have a program to run. I have to train students. My job is to pay people, get them trained, get them out there, get them working for whoever they want to work for. It's cute that the guy was like, no problem, just submit 4 or 5 times and I'll get through. Cool. If I was like 70 and it just, the world has changed, academia has changed.
That is
the
Yeah,
average age
if I
the
can
average age of PIs is
support,
going up,
if I
right?
can
So that's
support you
I
guys here,
disagree. I think it's
with I've been
always
going.
been
I
the same
went
way.
through similar
Yeah, that's a whole other discussion.
problems, and I just, I also started my own little company to generate some funding for projects that I did, but I honestly gave up on academia. Like, I work for a company, and I still have my affiliation, but I work for a company and I have my own company at the same time, because I just don't, it's just a waste of time. Like, all you do is deal either with bureaucracy or with grant writing for nothing. And then you went through all this training, right? Like Europe spent so much money on me to send me abroad and whatnot, so that I can sit at the desk and write grants and take care of bureaucracy, of stupid bureaucracy on top of it. Like this is such a waste
Yeah,
of time.
our
It's
university
so
actually has somebody who's dedicated to writing grants only, and they come and help every professor polish up their grants.
they don't write the
So I
grants.
just want
They
to, yeah,
just
I don't,
look if you have all the paperwork in place.
I don't want to poop. I don't want to poop too hard on academia. There's obviously some major problems within modern Western academia, and everything you said. I've become a manager and a grant writer, and you know, I am disconnected from the front line. I
You're
was a
underpaid. You're underpaid.
absolutely. I need, you know, I was once a phenomenal experimentalist, if not the one of the top in my generation. And now I'm just some dude who sits in his office and like reads the Guardian newspaper for like 8 hours a day. But so I get all that, but there is a silver lining, and that's, you know, there's not many bodies still out there. There's no Bell Labs anymore. There's no real national lab program in the US. It's mission goal driven for weapons program.
I was
You know,
just gonna say there's still
this
DARPA and ARPA
yeah,
and
yeah, yeah,
those
for
things,
sure, for sure. But like
but that's it.
this understanding how the interior of an ice giant works, there's not many environments we could have done this. Now, should we be better funded? Yes. Should access to be money be better? Yes. Does the federal government waste loads of taxpayers' money on stuff that shouldn't be wasted? All this, absolutely. Um, should NASA be investing in more fundamental research? Absolutely. Um, you know, academia has loads of problems, and it's made me really think about alternatives. But there's still something very liberating about being an academic and spending 4 years smashing your head against this problem. You know,
It's a
yeah,
very real. It's a very real reality, and it's one that kept me away from academia my career. And I did with 18 years at IBM Research. I watched it go closer and closer to the bone, and to the point where industrial research became more business development. And lo and behold, here I am in the defense industry. So yeah, it's a very real issue. We had a speaker, raise the point recently about all this, cryptocurrency wealth that's accumulated, and are any of these billionaires doing anything interesting with it? And she seemed to have, at least a perspective and some optimism about NFTs for fundamental research as a new funding vehicle. But
yeah.
yeah,
I love how I
I
get the
just want to
mic.
offer that if anybody out there is listening to this conversation, they're just thinking of dropping out of academia before, after listening to it, you're free to
Sure,
you're free to
surely,
contact me because, I would be happy to discuss in depth what the whole process is like and the pros and cons. I mean, one pro is that you're interacting constantly with students, right? And
yes.
that gives you that beginner mindset. As you get more and more sort of canalized in the thinking of your discipline, you stay fresh and current because you're forced through interacting with them to see things through, fresh perspectives. And it also forces you to kind of really stay current outside your own little bubble, and really you get opportunities to give talks all over the world and to interact with other people who are focused on the same kind of problem that you're focused on all over the world. I mean, there's a lot of really great things about it as well.
Hell yeah.
That was a great. That was a great statement. I mean, I'm hoping anyone that heard the whole talk would be like, I want to be a scientist and not I'm dropping out of academia. I was hoping that was the general end, but
There was so much
A lot
nerd
of science.
enthusiasm throughout the talk that I
I'm
guarantee that is what 95% of people
but
who
academia
will
has
well.
hear
its
this in
problems.
the
Like
I'm
future
we're
are
doing.
going
adults
to.
here. We're not hiding
I'm
anything.
doing. I'm doing basic research in companies, and I'm sorry, but everything that we got funded at academia was boring bullshit research, like just tiny incremental.
Yeah, but I would disagree.
And about fundamental stuff was not funded.
So in part, I agree to that statement, but look, the problem is this, and I'm torn because I've got the startup world and my startup hat and blah. But if we all dropped out of academia, who the hell is going to train these young folks to come and work in our startups? The startup culture.
I'm training them at the start. I'm training them.
Yeah, I don't know. Like as you said, as the previous person who was speaking, that the perks of academia are you have young blood coming through every year. No startup has this culture. And actually, one of the great things about, especially at UNLV, we have some of the most, socioeconomical diversity, ethnic diversity. It's a tapestry, a mosaic of people. Some of my group members that are actual superstars, they would have never made it beyond UNLV at first. They will become world leaders, but the startup culture, from what I've experienced shortly, is very aggressive, and there's something about a good state school in a state where people who've had underprivileged lives get access to professors like myself, and they realize in their early 20s that actually they've got the capacity to grow into a remarkable adult to contribute to the knowledge of society. And so academia has its problems. It's shit. That's not. I've already had 2 drinks. So, but there must be a place. There must be an environment where we can culture things. And the danger of startups is driven by capitalism. It's driven by money. Where academia, you can spend
cool. I'm sorry, so it's cool, and so is the education. And I'm sorry, academia is way more unfriendly for women and people of other races than and that's what's in a lot of.
I agree. Like I'm a brown man. Like I come from a refugee. I appreciate all this. I agree with you all of this, and so I would like to change it and improve it. If I burn this bridge, I will improve. I will help to be part of the change the grain. So I agree. It's very tough in physics. It's very tough for women. The gender bias is uncomfortably staggered towards white men. I get all this, and so
I'll see myself out. I saw the door on the way in.
So I promised to cook for my whole family who's sitting downstairs eagerly waiting for this conversation to finish. So
of course,
last 2 questions, and I'm going to get. And next time we should have just a conversation about the failures of capitalism. I will call in and give him my 4-hour rant.
No, thank you.
Yeah, that would be awesome.
I'm sorry it was so controversial about the
Oh, I love it. I love it. I wish
that's a Friday night session.
Forget about science. We should have talked about this.
Commiserating. I think commiserating.
Who cares about quantum mechanics?
Oh, and we could dish on industry endlessly, no doubt.
Hold my beer, please.
Well, at least from my perspective, I found that like for really cool projects that are very unlikely to be funded by government, I found private investors are willing to give you like 100K, 200K much more easily than the government, and then that allows you to do that proof of concept, that critical data set, and then the government's willing to listen. And I heard this years ago, like a decade ago, from Craig
also,
Venter.
I want to say that universities help professors find those private donors.
That's right. Yeah. So to be fair, it wasn't a university funded incubator program. But that's still something that is.
I just want to say something. We pay tax dollars. I would like my tax dollars to contribute to the wealth of knowledge. It shouldn't be rich people who are entitled, who have side hobbies in sciences, paying for this stuff. We as the population, we pay a lot of tax in this country. You don't get much buck for your tax. It's not like Europe where you get healthcare and everything else. I would like my damn tax dollars to be paid towards sciences. I don't want I don't want the charity of a rich man or woman, it's mostly white men, to pay for my work. I will pay
charity is no substitute for properly taxed wealth, and we need to rebalance the ecosystem.
All right, comrades.
That's right.
Money.
I wish you could see my Lenin poster in my bedroom.
That's awesome.
But seriously, why do we have to rely on the charity of an individual to fund fundamental
Yeah,
science? We pay our taxes. We should damn well invest in this stuff, and it's good for everyone.
yeah. It's just
You know,
unfortunate it has changed from what it was historically to this is what it seems to be like right now. And you said that academia was changing, and this is kind of how I see it changing. So.
Well, I worry about your domestic obligations
Yeah.
compromising your ability to return.
I think we really do have to do a part 2 of
Oh,
this.
definitely.
Yes.
I would love,
Yeah.
I would drink much harder liquor for part 2.
Okay, great. We should make it
That'd be,
we should make it an event.
I would
Yeah.
love.
So
This was
thank you.
phenomenal, folks.
Yeah, thank you so much, Ash, and let's chat again. And yeah, this was an amazing room, really outstanding. And apologize for being harsh, but when I get like annoyed about something, you know,
No, I'm pumped.
I'm
I'm
still
pumped. I'm pumped.
Portuguese.
I'm pumped. I
Uh,
love all this rhetoric. I think, but next time we should do a game where we all drink a bottle of whiskey,
Yes.
and then we come,
Pints of
to the chat,
Yeah, pints of
and then we
that's
see
that's
who.
how we'll solve all the world's problems.
That's right. Last human standing. That's a good game to play.
I'll be
Really
sporting
quick,
a single malt.
before you depart, it's fascinating. There's in chat. There's a quick question on the you're asking for your thoughts or comments of the tungsten and molybdenum, like as the metals as cofactors. Any thoughts? Any comments or?
A fascinating question. Sorry, just to bring it back to the science. What was the exact question? I didn't. Tungsten, tungsten based, nitrogen based, molybdenum, iron based.
Yeah, it was asked by
So I
Dr.
don't
Lee,
quite
who
understand.
also was eating.
Speculation about metals and
Maybe
cofactors
for
and
the
extreme
second part.
thermophiles.
Yeah.
Oh, so sorry. This is the idea that noble metals in extremophiles. When he says extreme thermophiles, does he mean extremophiles? I don't quite understand the exact question. I think
Hyperthermophiles.
hypertherm. I don't even know what that
Well,
is.
that's a thermophile that's probably at above the boiling temperature of normal boiling temperature of water and
A pump,
extreme
Yeah.
the
pressures.
pump's thermophile.
Yeah. So I'm thinking about socialism. So going back, this idea of a noble metal dopant within a water framework, is that what we're asking here?
I
I need
Well, can
think,
we
yeah.
ask it, or should that be a part 2?
exactly,
Yeah, I
exactly.
was
Good place
thinking
to
If
that.
you,
cut it
I'm
off.
gonna
So,
tell you right
Yeah.
now. If you invite me back for part 2, I'll beatbox the whole hour and a half.
hell
Okay.
yeah.
I'll do it in song format. There you go. And so,
Thank you.
Okay, make sure everybody to give Ash a follow, and please follow the club at the top by pressing the greenhouse button. And thank you to Ash for joining us, and everyone else for the
thank you
wonderful
so much,
Yeah,
question.
everyone.
thank
It was
Thank you very
Yeah,
much.
Thank
excellent
you.
so much
Thank
fun.
you.
So
thanks.
much
sharing.
Thanks,
fun.
Ash.
Come back
Appreciate it.
Boom.
anytime.
Ciao, everyone.
Bye.
Bye.
Bye
Bye.
bye. Take
Ciao,
care.
Good
ciao,
night.
ciao, 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 ciao.
Yeah, thanks everyone. This was such a great discussion for asking all these great questions, and follow the club, as I already said, and we'll have tomorrow Dr. Liang. It's actually from a company, and she will discuss about carbon negative production of acetone and isopropanol, and then we'll have on. Oh no, I'm sorry. That is on Wednesday. Tomorrow we have Dr. Len's human evolutionary distinctiveness. You know, you heard probably that we now know the whole genome, so it's a study about more evolutionary biology in the terms on how we as a human distinguish. It's not too many genes, but there are few, and it's an interesting evolutionary room. And then Thursday we have a room about ADHD and hoarding related neuroscience. And on Friday we will have probably more kind of a roundtable discussion room or another hallucinogen room. We are still coordinating the dates, but I prefer actually on Friday night to have more kind of a round table. We can, if you have suggestions for something you want to discuss, please go ahead, suggest. And then other than that, we'll have, you know, like we had last Friday, it was pretty good. Went for like 5 or 6 hours the room, so it was pretty good. And then on Saturday we have at 1 p.m. EST Dr. Marco Pettini from Italy, talking about his physics research, quantum mechanics, long distance electrodynamic intermolecular forces. That is the paper that was up on last Saturday.
Yeah, yeah. Make sure you don't pin the other person's one up to swap it around this time. Yeah.
Okay,
I think
thanks for this
unfortunately
wonderful.
that overlaps with Paul's room on time.
The Saturday room? Yeah, there's nothing I can do about it. It's more up to the guest speaker when they want to come and speak. So, yeah, we'll have a recording and everyone can listen to it that can't make it to the room. So, it's really more up to the speakers. I'll give them like some guidance on when we usually, if I try to get them to the 9 p.m. schedule, but if they are from Europe, it's pretty, you know, not possible. And if they don't have time during the week, I'll try to get them on the weekend. So, yep. So, yeah, he seems to be really, like, Marco Pettini is a really nice and really amazing scientist. But if you want, you can just listen to the recording. It's really up to everyone here. And on Sunday we have our weekly recaps. If you like miss rooms, we'll have like about an hour weekly recap room to summarize. And if you have questions or so, we try to answer them. It's just like a short summary of the week. So thank you everyone. Have a good evening, and thanks for this great evening.
Thank
Bye.
you,
Thanks,
Katerina. Good night,
everyone.
Thank you,
everybody. Bye
Katerina.
bye.
Thanks,
Bye.
everyone.
Bye.
Good night.